In the previous class, we completed few additional properties on DFT. Now let us move on to the property number 9, which is modulation property, and the statement goes like this: the DFT of x1 of n is x1 of k and the DFT of x2 of n is x2 of k. Then according to modulation property, we need to prove that the DFT of x1 of n into x2 of n gives us 1 by n x1 of k circular convolution with x2 of k. In order to prove this property, the basic step what I have done is, I have taken the DFT equation. So DFT is given by x of k, which is equal to summation n ranges from 0 to n minus 1 x of n into e power minus j 2 pi k n by n, where the range of k is from 0 to n minus 1. So in order to prove this, what let us do is, let us take this product term as x3 of n. If that is x3 of n, then here the sequence becomes x3 of n, and here also the sequence becomes x3 of n. If DFT is applied to x3 of n, we get x3 of k. So this becomes x3 of k. Now in this equation, what is x3 of n according to the given statement? X3 of n, according to the assumption, it is x1 of n into x2 of n. Let us make the substitution here. Okay. So if I make the substitution, x3 of k will be equal to summation n ranges from 0 to n minus 1 x1 of n into x2 of n into e power minus j 2 pi k n by n. Now looking into this equation, we know x1 of n and x2 of n are nothing but the sequence. So instead of these, what I can do, I can write the IDFT equation for these two sequence. So if I write the IDFT equation in terms of x1 of n and x2 of n, so it can be written as x3 of k, that is equal to summation n ranges from 0 to n minus 1. I am writing this as it is. So the IDFT equation for this is 1 by n summation. So I will take the other variable, m ranges from 0 to n minus 1 x1 of m into e power j 2 pi n m by n. So this is the IDFT equation for x1 of n. Since everywhere we have n, in order to avoid confusion, instead of writing the IDFT equation in terms of n, I have written it in terms of m. Similarly, let us write IDFT equation for this also with the variable p. So if I write, I can write it as 1 by n summation p ranges from 0 to n minus 1 x2 of p into e power plus j 2 pi p into n divided by n. So this completes the IDFT equation of x2 of n. Now this is left out as it is, write down that as it is, that is e power minus j 2 pi k n by n. So this is done. Now what I can do is, let us just rearrange the summation and let us rewrite exponential terms aside, and I can multiply these to 1 by n and 1 by n. So rewriting this particular equation, I can write it as 1 by n square into summation m varies from 0 to n minus 1 x1 of m into summation p ranges from 0 to n minus 1 x2 of p. So next I need to write this particular summation, that is summation n ranges from 0 to n minus 1 into e power, what is the exponential power in the first term? It is j 2 pi n m by n into e power, the second element is here, j 2 pi np by n into the final term e power minus j 2 pi kn by n. So this is the equation after rearranging the summation. Okay. Now looking into this equation, we have 3 exponential term. So I can rewrite all those exponential term using a single exponential term by taking common factor in this particular term. So let us rewrite. So if I rewrite, x3 of k will be equal to 1 by n square, summation m ranges from 0 to n minus 1 x1 of m into summation p ranges from 0 to n minus 1 x2 of p into summation n ranges from 0 to n minus 1 e power. So what are the common factors which I can take? I can take the common factor as minus j 2 pi n by n. Here also you have j 2 pi n by n. Here also you have j 2 pi n by n. So let us take e power minus j 2 pi n by n as the common factor. So if it is done, so what is the term left out here? K is left out here, minus m is left out here, and minus p is left out here. So let us tabulate that inside the bracket, that is k minus m minus p, and let us term this as equation number 1. Now in this equation, let us consider only the third term and let us try to simplify that, and later let us substitute in equation 1. So consider third term in equation number 1, that is summation n ranges from 0 to n minus 1 e power minus j 2 pi n by n into k minus m minus p. Now let us deal with respect to two cases. So the first case is, in case 1, let k minus m minus p be equal to n in this particular third term. If so, I can write it as summation n ranges from 0 to n minus 1 e power minus j 2 pi n into n by n. Now I can cancel n and n, and we know for all values of n, e power minus j 2 pi n tends to 1, or e power j 2 pi is also equal to 1. So if I rewrite this, I can write it as summation n ranges from 0 to n minus 1. Instead of e power minus j 2 pi, I will write it as 1 to the power of n. So this is similar to the standard formula, which is nothing but the upper limit minus lower limit plus 1. So if I substitute that, gives us n minus 1, the upper limit, minus the lower limit plus 1. So now I can cancel minus 1 with plus 1. So finally we get n. So whenever this term is equal to n, in third term we get the value as n. So this is in case 1. Let us move on to case 2. So in case 2, let k minus m minus p be not equal to n in the third term. Again, if I substitute the same thing in the third term, we can rewrite it as summation n ranges from 0 to n minus 1 e power minus j 2 pi by n into k minus m minus p to the power of n. Again, this is similar to the standard formula a power n, so which is nothing but equal to 1 minus a power n divided by 1 minus a. Let us apply the same formula to this one. So if we apply and rewrite, I can write it as 1 minus e power minus j 2 pi k minus m minus p divided by n divided by 1 minus e power minus j 2 pi k k minus m minus p divided by n. Now looking into this equation, what we can do? I can cancel n with n. If we cancel n with n, what is left out here? We have only e power minus j 2 pi k minus m minus p. So for all values of k, m and p, what happens to the exponential term? The exponential term tends to 1. If the exponential term is tending to 1, in the numerator we will get only 1 minus 1. So what is 1 minus 1? We know it is nothing but equal to 0. So 0 divided by anything gives us 0. So I will directly write it as 0. So the same simplification we have done in circular convolution property also. Okay. So this is with respect to case 1 and case 2 of the third term. Now let us write it aside and then substitute in equation number 1. If I rewrite it, I can write it as summation n ranges from 0 to n minus 1 e power minus j 2 pi n by n into k minus m minus p. This will be equal to n when k minus m minus p is equal to n. That is k minus p minus is equal to n, and it is equal to 0 when k minus m minus p is not equal to n. Now let us substitute the same thing in equation 1. So instead of this entire third term, I can rewrite it with n. So if I rewrite the equation, substituting in equation 1, x3 of k will be equal to 1 by n square summation m ranges from 0 to n minus 1 x1 of m into summation p ranges from 0 to n minus 1 x2 of p into n. Now I can cancel n with n. So if we rewrite the equation, it will be equal to 1 by n summation m ranges from 0 to n minus 1 x1 of m into summation p ranges from 0 to n minus 1 into x2 of p. Now let us take substitution for p and let us see what happens to the second term. So if I take substitution, let k minus m minus p be equal to L n, where L is equal to minus 1. So if I substitute it here, it will be k minus m minus p, which is equal to minus n. Now I need to find out what is p. In order to find out that, k minus m plus n is equal to p. So looking into this, what we can make out, only at one value of p we get the value for x2 of p. So there is no need to write the summation. So let us substitute the same thing in this particular equation and let us continue the simplification. Therefore x3 of k will be equal to 1 by n summation m ranges from 0 to n minus 1 x1 of m into x2 of, what is the substitution for p which we have taken? This one, that is k minus m plus n. Looking into this equation is similar to circular convolution equation. So let us rewrite this and see what we are going to get. So x3 of k, which was nothing but equal to dft of x1 of n into x2 of n. This is equal to, if I rewrite this, I can write it as 1 by n summation m ranges from 0 to n minus 1 x1 of m into x2 of k minus m of n. Okay. So this is nothing but the standard equation for circular convolution, this entire part. So now instead of writing like this, I can write it as 1 by n into x1 of k circular convolution with x2 of k. That is, the DFT of x1 of n into x2 of n gives us 1 by n x1 of k circular convolution with x2 of k. This is about modulation property. This property is very much similar to circular convolution. So, if you learn one property, it is very easy to remember the other property. After modulation property, the next property is circular correlation. So, in circular correlation, we have two types of circular correlation. The first one is circular cross correlation and the other one is circular autocorrelation. So, autocorrelation is nothing but if you take one signal and if you find out the similarity in that particular correlation is called as autocorrelation. So, if we find out the similarity between two different sequences, that is if you take x1 of n and x2 of n, and if you find out the correlation, then the resultant correlation is called as cross correlation. The statement goes like this for circular correlation, that is if x of n DFT is given by x of k and DFT of y of n is y of k, then Rxy of n tilde, so this symbol is called as tilde. So, if we apply DFT to this, gives us Rxy of k tilde, which is equal to x of k into y conjugate of k, where Rxy of L tilde is nothing but circular cross correlation, which is given by the expression summation n ranges from 0 to n minus 1 x of n y conjugate of n minus L of n. So, this is the expression for cross correlation. Okay. Now, taking this equation, let us try to prove we are going to get this. Okay. Now, I have considered the circular cross correlation equation. Y cross correlation, we are using two different sequences. One is x, the other one is y. So, it is circular cross correlation. Now, in this equation, let us replace y conjugate of n minus L of n by y conjugate of minus L minus n of n. So, instead of this term, let us take this substitution. Okay. If I take that substitution, Rxy of L tilde will be equal to summation n ranges from 0 to n minus 1 x of n into y conjugate of minus L minus n of n. After substitution, we get this equation. Looking into this equation, it is similar to circular convolution. So, if I rewrite the standard form of circular convolution for this, I can write it as Rxy of L tilde, that is equal to x of L circular convolution with y conjugate of minus n. So, this is the equation. So, the right hand side is nothing but it is similar to circular convolution. You can rewrite circular convolution like this also. Now, to this let us apply DFT and see what we are going to get. So, if I apply DFT to this, I can write it as R xy of L tilde, which is equal to, we know convolution in time domain is nothing but equal to multiplication in frequency domain. So, if I apply DFT to this, so I can write it as DFT of this will be equal to x of k. Now, I need to find out the DFT for y conjugate of minus L. Since I do not know what is the DFT of y conjugate of minus L, now let us find out the DFT for this. So, let us term this particular equation as equation number 1. Okay. So, if I write the DFT for this, the DFT for y conjugate of minus L is equal to summation L ranges from 0 to n minus 1 y conjugate of minus L into e power minus j 2 pi k L by n. Instead of n, since I had L, I have written it as L. Instead of x of n, so this is nothing but the DFT of this particular sequence. Instead of x of n, we have y conjugate of minus L. So, instead of x of n, I have written y conjugate of minus L only. Okay. Now, if I continue this, let us take a substitution. Let n be equal to minus L. So, if n is equal to minus L, I need to check what are the limits which we are going to get with respect to n. So, if L is equal to 0, n is also equal to 0, correct? Similarly, if L is equal to n minus 1, then n is equal to minus L, so it becomes minus n minus 1. Now, let us substitute the same thing here. So, if I substitute the DFT of y conjugate of n is equal to summation n ranges from 0 to minus n minus 1 into y conjugate of n. Instead of minus L, I need to write it as n. So, according to the substitution, into e power j 2 pi k n by n. After substitution, this is the equation which we got. Now, in this equation, if I continue the simplification procedure, so one thing which I can observe is, so the range of n is varying from 0 to minus n minus 1. The range from 0 to minus n minus 1 is similar to the range of n from 0 to n minus 1. So, if I rewrite this particular equation, we can rewrite it as DFT of y conjugate of n is equal to summation n ranges from 0 to n minus 1 into y conjugate of n into e power j 2 pi k n by n. Okay. Now, let us take conjugate for the entire term. So, if we do so, summation n ranges from 0 to n minus 1 y of n e power minus j 2 pi k n by n, the whole conjugate. Now, looking into this equation, this is similar to the DFT equation. So, instead of x of n, we have sequence y of n. So, this is nothing but the DFT of sequence y of n. So, if I rewrite this, what am I going to get? So, the DFT of y of n is nothing but y of k according to the statement, the whole conjugate. This can also be written as y conjugate of k. Now, in equation 1, I was not knowing the DFT for this. Now, we found out the DFT. So, let us substitute the same thing here. So, if we substitute, so substituting in one Rxy of L tilde will be equal to x of k into y conjugate of k. So, this was the thing which we needed in circular correlation property, that is Rxy of L tilde represents the circular correlation, that is cross correlation, which will be equal to x of k into y conjugate of k. So, this is the standard proof for the property circular correlation. Now, we completed circular correlation property. We have one more property, that is Parseval's theorem. So, if we complete that, all the properties in module 1 will be done. So, then we will start solving problems on all the property. So, thank you for today's session.